So it's a pleasure to introduce Dr. Andrew Zammit-Mangion. He's one of the leading experts on spatial and spatial-temporal statistics, especially in applications to large-scale data and environmental climate science. So Andrew is an associate professor with the School of Mathematics and Biostatistics at the University of Wollongong in Australia. He's an expert on spatial temporal models, but more recently, he's also been looking at novel ways to combine ideas in deep learning with spatial temporal modeling. This is a very long list. I'm going to shorten it. So Andrew has a lot of awards. Just to mention a few. SBI paper, Engineering and Biosciences, Axel Sharabi Young Researchers Award, the Early Investigators Award by ASA, the ASA Outstanding Statistical Application Award, and he's currently a member of NASA's Orbiting Carbon Observatory. He's also published co-authored a book with Christopher Whitley and Neil Cressy on spatial temporal models. And
that was a long introduction. Okay.
And today we'll talk about neuro SBI for spatial and spatial temporal statistical models.
Okay. Thanks a lot, Anne. So first of all, I'd really like to thank Mikhail and Anne for inviting me to this really wonderful workshop. So great to see so many people whose work I've read but never met in person. So I'm really happy to be here. My talk's a bit different from the previous ones, which were more on methodology. Here, the brief from Mikhail was talk how neural SBI helped us in the field of spatial and spatio-temporal statistics. Now, to get to that point, first we must do a crash course in spatial and spatio-temporal statistics, because I'm sure at least some people here wouldn't know what that is. And then we'll talk about a very simple way of doing neural SBI, which is point estimation. Personally, I think everybody should start with point estimation before going to full posterior distributions, and then we'll talk finally about some applications. So about 3 parts, 15 minutes each part, sort of thing. All right. So I've worked with many people on neural SBI in spatial and spatio-temporal. My former PhD student, Matthew Sainsbury-Dale, Raphael Hooser at Cowes, Jordan Richards, now in Edinburgh, Bao, my former PhD student, Chris Weichel, and Noel Cressy, who are all in statistics. All right, so let's start with spatial and spatio-temporal modeling. This slide is very similar to what Kyle showed, actually, but Kyle was saying, listen, you have simulators for all these things. I'm going to say we've got data for all these things, which are space and time, which have some spatial or temporal component or both. And what we want to do in spatial and spatio-temporal statistics is really try to analyze these data for a variety of reasons. There might be some parameters which might tell us something. We want to estimate those parameters. We might want to gap fill. We'll see a lot of that, or we might want to forecast what's going to happen in the future. Okay? So a couple of projects which I've worked on. This was a project which I started at the University of Bristol in the UK, where we wanted to quantify the sea level rise contribution of Antarctica. You might think it's quite a simple problem. There's lots of satellites which give us data, but actually it's a very difficult problem because the satellites don't tell you what's happening to the ice sheet. They give you like a total altimetry reading of precipitation plus ice sheet plus firn compaction. There are other processes like the isostatic adjustment, which you need to take into account. So what we did was kind of this big data fusion model, an underlying multivariate spatio-temporal model, which I'll talk a bit about later, and then we make inferences. There are physical models, there are regional climate models. They're actually very poorly validated for Antarctica. Okay, so this is why we can't rely wholly on regional climate models over there. This is another big project that I've worked on for many years. It's also a multivariate space-time model, which this time incorporates physics in terms of atmospheric transport. This is what we call a flux inversion problem. On the left here, I'm showing you flux. So that's actually the rate of carbon dioxide emissions in the United States in January, and then I'm switching it off in February. What I'm showing, that's one process, space-time process. On the right-hand side, I'll play the video again, is what's happening to the carbon dioxide that you are emitting. It goes all around the world. But what we observe is, points, actually column averages, if you have a satellite of this, but we really want to get back to the emissions, right? So that's a big inverse problem. There's physics in there. There's lots of uncertainties, which we model using spatio-temporal models. All right, this you can actually lead to real science, although these are statistical models which sometimes are disconnected from reality. But in the specific case of carbon dioxide, we actually have physics and what I'll call descriptive models, which I'll describe later. In this case, we contributed to our report in support of the United Nations Global Stocktake a couple of years ago. All right, so briefly, again, for crash course purposes, there are two classes of spatial and space-time models. The first is the descriptive. Think of no physics. I just want to interpolate between points. That's descriptive. And then dynamical. Okay, so only for spatio-temporal. When we're talking about dynamical, we have some understanding of how this process is evolving over space and time. All right, so let's start off with the descriptive approach. The thing you'd hear the most if you go to a spatial statistics class is Tobler's first law of geography. It relies on this notion that things closer together are more similar than things further apart. Okay? So if you don't really know anything about the process and you want to interpolate, you're going to say, well, things closer together co-vary more than things further apart. So we'll talk about the covariance functions. So now this, of course, isn't always the case. In real life, things are more complicated. But as a starting point, Tobler's first law of geography is not bad. Okay? It can take you a long way. All right. We always consider hierarchical models. So Stefan was saying, we always need to consider hierarchical models. This is the norm in spatial and spatial statistical models, at least 2 layers. You've got observations, which are recording the true process, and you've got some error. And that is the first layer. We call that the data model. And then you've got your true process. And this is really what you care about. I mean, traditionally in statistics, you model the observations, but we really care about the true process, not the observations. And there usually is some trend term. This would be the x beta in your linear regression, for example. And then this is where you have this correlated spatial or spatio-temporal process. Okay. So we generally define our process y over space and time as being continuously indexed. More often, we say time is discrete, makes things a bit easier. And we use y for the process, definitely for this slide back, and z for the data. Okay, so we make a distinction between z and y. Z is what you observe. Y is the process defined everywhere. Okay. So what does a data model look like? The simplest data model you could have is something like this, which is saying that Zij, which is the data at some spatial location I and time point j, is just the process at that location plus some measurement error. Right? And that measurement error, typically Gaussian, okay, but you could have more complicated error models if you want to. Okay? Now, what do we do for the process model? Okay, so space and time, there usually is this large scale term that I talked about earlier, and then we've got this random term here, which is eta, which gives you the correlations in space and time. Now, this, what we call this process mean or the large scale term is typically something like x beta. So if you're modeling temperature, let's say y is temperature, x could be elevation, and beta could be the coefficient associated with elevation, typically negative, because the higher you go, the colder it gets, right? But elevation doesn't totally explain temperature. There's some residual variability that you need to take into account, and that residual variability is usually correlated in space and time. So you try to describe that with a descriptive process if you have no other information through the covariance function. Okay, so this is the most important quantity in spatial and spatio-temporal statistics. It is how the process at space s and time t correlates or co-varies with the process at space location r and time point u. Okay. Now there are some parameters in there. This is the connection to neural SBI, which we'll get to later. Theta, that determine what this covariance function looks like. And there's also beta there, which usually that's an easy quantity to estimate. Okay, just to give you a quick picture of what this looks like, we have some data points, which are the black dots. We have think of this as temperature. We have a curve. We don't know what that is, but we're going to try to fit a curve through to these data points over there. If we say that the covariance function looks like this, and you apply some very simple equations, a Gaussian process regression, Kriging, optimal interpolation, they all do the same thing. What you get is a prediction and also a prediction uncertainty between those observations, okay, corresponding to the process. If you change the covariance function, all I've done is change the behavior at the origin over there. You get a totally different. Well, the prediction is quite similar, but the uncertainty quantification definitely changes a lot. Okay, so the covariance function is really important actually for uncertainty quantification, right? So just oscillating a bit between those two, you can see how much the covariance function affects. So when we're estimating theta, we're generally estimating this shape of this covariance function, okay? All right. So now let's move on to the dynamical approach. And this only applies to spatio-temporal models. So the biggest problem with the descriptive approach is that it's pretty naive. Okay, you're saying that things close together are more similar than things apart, but that will only get you so far. If you've got some richer understanding of what is going on, you can use adopt a dynamical perspective, which you can express through conditional distributions in a statistical framework. Okay? So we still have the data model and the process model. And what we're going to do now is consider the joint distribution of the data given the process. And the typical assumption, which does hold in many situations, is that you're conditional on the underlying process, the data are independent. Okay, so the error is IID, or at least independent, not necessarily identically distributed. And what that means is that this joint factorizes as a product of conditionals, which is nice to work with. And then the other assumption one usually makes is that the joint distribution of the process factorizes in this form. So we put on a Markov assumption for the process. The process at time t, conditional on t minus 1, is independent of what happened beforehand. Okay, that's the Markov assumption. And there again, this is where we'll get to neural SBI pretty soon. These are where the parameters appear. They appear in the process model. They could also appear in the data model in terms of the measurement error variance, for example. Okay, now the challenge is, yeah, sure.
The top one?
Yep.
Usually assume it's like given YT, like each individual YT as opposed to like all YTs.
Yeah. Yeah, actually, that you can even decompose that further, but I've kept it a bit more general in this case. Yeah. All right. So the challenge here is how do we specify these conditional models? So we've got physics to help us explain some of that with use it. If we don't, we can still adopt some kind of generic dynamical model, which seems to work in most cases. And one of the most popular ones, which I'll show you later in an application, is the integral difference equation, which takes this form. Okay, so what you say is that the process at yt is a convolution of the process at yt minus 1 with some kernel m. Right? Now that won't explain everything, so you always add on a descriptive space-time process on top of that. Okay. If you discretize this over space, okay, so think of having a fine grid, okay, you can discretize an integral in 2 dimensions, you can do that pretty accurately. You get something like this, okay? So what you get now is this kind of these kernel quantities which depend on some parameters, and those parameters determine the dynamics of your system. So again, just to give a picture of what's going on, if this kernel is very narrow, you've got a lot of persistence. Okay, in time. So these are, by the way, these are called Hofmöller plots, where time goes down, so it's increasing from top to bottom, and space is going from left to right. Okay? So this is one-dimensional space to keep it simple. Right, so you've got a lot of persistence. As soon as you make the kernel a bit wider, it starts to diffuse more. Okay, so you get like broader patterns. As soon as you make the kernel asymmetric, you get flows. Okay, in this case, from left to right. And make it asymmetric the other direction, you get flows from right to left. Okay, and we can make these kernels spatially varying as well, and even spatio-temporally varying themselves. Okay, and we want to then estimate how these kernels are changing in space and time. Now, this becomes a really complicated inferential problem where neural networks can really help us. Right. So, what are the challenges? So models in space and space-time generally have a really large latent dimension. Okay, think of the process at every pixel in space and time as being a random variable. Okay, so really large latent dimension, but a few parameters. So the covariance function, for example, can be described using few parameters, typically at least 2 or 3. If you want non-stationarity, maybe a bit more. But even the kernels, they don't need to be in a dynamical system. They don't need to have millions of parameters. Okay. So inference often needs to be done with big data, irregularly spaced data. That's a challenge for neural network architectures, which we'll see later. So what we usually do is MCMC, or some quicker approximation like variational Bayes. Sometimes the likelihood function is intractable. If we're talking about models for spatial extremes, for example, or POTS models, which we'll talk about later, likelihood function is intractable. And many times we've got satellite data. We want to do some inferential analysis today on 1 million data points. We want to do the same thing tomorrow and the day after and the day after, right? So we need to do inference many, many times as new data becomes available. And it's always the same optimization problem. We're just changing the data set. Okay, so this is where neural amortized Bayes estimation can help us. All right, so we heard this word amortization. If you haven't heard this word before today, I'll just explain it very quickly. So amortization is the action or process of gradually writing off the initial cost of an asset. Okay, so imagine you buy a season ticket for something. It costs you a lot of money, but if you use the public transportation every day for a long time, then eventually you'll make a profit, right? So in the context of neural networks, the initial cost is that of training the network. That usually takes a lot of time, a lot of effort, relatively speaking. But once you train it, you can apply it to new data almost instantaneously. Okay? It doesn't cost a lot of power or time to run a neural network in a feed-forward fashion. Right. So we heard a lot about posterior distributions today. I said earlier on that I think we should always start off with point estimation for the simple reason that it's much easier to train neural networks for point estimation, just to estimate a single quantity than to estimate something related to a full posterior distribution. Okay, and personally, I've never, in spatial and space-time, I've never coded up a neural network which didn't work straight away when it came to point estimation. Okay, because it's just a very simple problem. All right, so what are we doing here? So we have a neural network which takes in data and returns a point estimate. Okay, so if you have 5 parameters, the output of the neural network is simply 5-dimensional. Okay? And the data could be whatever, 1,000, million dimensional, maybe not 1 million, but really high dimensional. Okay, and what we can show, and I'll show you this with a little bit of math in the next slide, is that this point estimate is just not an arbitrary point estimate. It's actually a summary of the posterior distribution. Okay. So let's see why that happens. So let's start off with some loss function. Okay, I'm sure you've all seen loss functions before. You've got some true parameter theta and an estimator theta hat, which is a function of the data. It's an estimator is a function of data. An estimate is the output of the estimator. All right, so we've got this loss function. Think of the mean squared error. Okay, so theta minus theta hat all squared, for example. Okay. Now that in of itself doesn't really help us when designing an estimator, because theta could be anything, z could be anything. So what we do typically is construct a risk function. So the risk function is the average of this loss for a given theta over all possible z. Right, so for every theta, you will be given a risk, and you can imagine sweeping theta across the parameter space and seeing what the risk looked like. And you can actually stop there and say, I'm going to choose an estimator which minimizes the maximum risk. That's called a minimax estimator, for example. But if you want to, you can go a step further, and we can consider what's called the Bayes risk, where we take an average of the risk over all the parameter space. Okay, the Bayes estimator is going to be that one which minimizes this average risk. And this is what I've written down in maths over here. Okay, so just as a picture here, so I'm proposing 2 estimators. I'm showing you what the risk functions look like for these 2 estimators. And just by looking at this picture, you'd say, well, theta hat 1 is definitely better than theta hat 2, right? The risk is lower for every value of theta. Actually, we would say theta hat 2 is inadmissible in this case. It's never better than theta hat 1. Right, so the risk function looks like this. If I wanted the Bayes risk, what I do is take the average. If I choose a uniform measure for our prior distribution, is just taking literally the average under the curve. And the average under the blue curve is less than the average under the brown curve, so you choose theta hat 1, okay? So when we find Bayes estimators, what we want to do is find a functional form for theta hat, which gives me the lowest average risk. We can think of it like that, yeah? So where the neural networks come in, we're going to say, well, theta hat is this really high dimensional mapping, right? It's taking its Z, which is really high dimensional. It's giving me a low dimensional output. Let's throw a neural network at it. That's what all we're doing. Okay, we can throw other things at it, and we've tried that, and they work as well in point estimation. You can even use splines if you have a very simple problem. But for really high dimensional settings, you can use neural networks. All right, so theta hat, our estimator, we're going to say it's a neural network. The neural network has got weights and biases, gamma. And now we need to find those gammas. And what we're going to do is minimize the Bayes risk. Now, the Bayes risk involves these two integrals, which is very hard to, you can't do it analytically. So what you're going to do is a Monte Carlo approximation. You sample from theta, you sample from Z given theta. This is the simulation-based part, which most of the speakers are talking about. And then you have a Monte Carlo approximation of this Bayes risk. Okay? So what you get is this Monte Carlo approximation, and then you're going to minimize this approximated Bayes risk with respect to your neural network parameters. You can use, of course, automatic differentiation, and what you're going to get is optimal parameter estimates, and on convergence, that estimator should be a Bayes estimator. Okay. All right, so if your neural Bayes, yep.
What is the size of the gamma?
Oh, it could be huge, million. Yeah. So your K needs to be really large, right? This is the K is your simulation budget, and this is, as someone said earlier, that is usually your bottleneck. Right? But in spatial statistics, simulation is actually relatively cheap compared to these other applications that we've been thinking about. So this is why we've got a very big simulation budget compared to galaxy formations and these other things. Right. Okay. All right, so a neural Bayes estimator will inherit the attractive properties of Bayes estimators, okay, subject to some conditions, but you've got consistency, asymptotic efficiency, asymptotic normality. You amortize the initial training cost, and your choice of loss function determines what your Bayes estimator is. So if you use squared error loss, your Bayes estimator is the posterior mean. If you use the absolute error loss, you get the posterior median. You can use quantile loss, you get posterior credible intervals, things like that, okay? This is what I'm saying here. You can also bootstrap a Bayes estimator, okay? It's a point estimator, so you can do parametric or non-parametric bootstrap. And if you want credible intervals, you just use the quantile loss function, okay? The workflow for what, in Bayesflow and many other frameworks, it's pretty consistent, irrespective of what model you have, unless you want to go to specialized models like Stefan was talking about before. But basically, it's always the same. You sample from some prior distribution, you simulate data conditional on the prior, you choose a loss function, you have a neural network, you train, and then you assess. Okay? And this is why software packages can be built around neural SBI, because the workflow doesn't really change that much between applications. Okay, so let's just look at this in action on a very simple problem. We've got a sample of size m from a uniform distribution with an upper bound theta when we want to estimate that theta. We're going to choose theta to be Pareto distributed. Why Pareto? Because in this case, we get a conjugate distribution, and we can actually know what the posterior median of theta in this case is, and this is the analytical form of the posterior median. So we actually know what it is in this case. It's of course nonlinear in the data, and it's a function of the prior. Right, so we're going to throw a neural Bayes estimator at it, and then we're going to train it by simulating lots of times from this model, and then we can see the sampling distribution. Okay, and And what I'm showing here are three sampling distributions. The green is the sampling distribution of the true Bayes estimator. The red is the sampling distribution of the neural network, which is now converged to a Bayes estimator. You can see they're exactly the same. The purple here is the sampling distribution of the maximum likelihood estimator. And I'm showing that because, especially in spatial statistics initially, people used to think that these neural networks are somehow targeting the maximum likelihood estimator, but they're not. Okay, you could be, the way you're simulating your parameters to train your network is inducing a prior distribution, whether you like it or not. Okay, so ultimately, you are going to have a Bayes estimator. And if you want to target a maximum likelihood estimator, you must use something like a 0-1 loss or something which approximates a 0-1 loss, because you can't really train with a 0-1 loss. Okay. All right, so I've got a few minutes left. Well, 15, 20? All right.
Yeah.
Good, so that's pretty much on time. So now we'll see how we've been using mostly, not always, neural point estimation in space and space-time models, and how this has helped us in various ways. Okay, right. So I'll be showing you lots of case studies, mostly pictures. In all cases, we verified the neural network outputs against ground truth methods such as MCMC, if we could. In all cases, the neural networks maybe took a few hours to train, and in all cases, inference was made in a few milliseconds after you trained the network. Okay. All right. I don't expect you to take note of these citations, but if I'll put the slides on Dropbox or Google Drive, and if you want to refer to any papers, these are the list of papers on which these results are based. All right. All right, so the first one is analyzing sea surface temperature. So the problem here is that you've got a satellite, in this case the VIRS, and it is giving you 1 million observations a day on sea surface temperature. They're very gappy, so lots of missing data, and we just want to fill in on a daily basis what's going on. All right. And sea surface temperature is actually very smooth, very well behaved. You can use a descriptive approach and get really good results. And this is what we're going to do through a Gaussian process at it. The Gaussian process has 3 parameters in this case. We've got rho, which is a length scale, sigma, which basically is giving you the amplitude, and tau, which is the measurement error variance, or phi scale variance, if you've got already an idea of the measurement error variance, right? So this is what a snapshot of one day could look like. And if we zoom in, okay, you can see a phenomenon that we call non-stationarity, right? So the spatial behavior in one part of the world could be totally different from the spatial behavior in another part of the world. This is why we need to estimate the parameters, not 3 parameters for the whole world. That would not be a good idea. This is the Brazil-Malvinas confluence zone, where you've got cold water coming up from Antarctica and warm water coming down from the Atlantic. Lots of activity, small length scales if we want to interpolate. On the other hand here, just west of the west coast of Australia, things are very smooth. Nothing much is happening over there. So the parameters are different, right? And so what we do actually is divide the globe into about 2,200 hexagons. We use a discrete global grid. And on each of those, we fit a Gaussian process and we predict what's happening in the middle. Now, fitting Gaussian processes is actually pretty easy. Okay, you probably don't need neural Bayesian inference for this. But still, if you want to do 2,200, you probably need an HPC for that, if you want to do that every day, right? While with neural SBI, we can do this, the whole globe, in maybe a couple of minutes on a standard GPU, okay? So it makes it just more available, more easier to do. Now, the architecture for this of the neural network is a bit non-traditional, okay? The data are irregularly spaced. You can't use a convolutional neural network for this. So we use a graph neural network. Another issue is that the irregularity is not the same. And if you train a neural network on a certain type of irregularity and you give it a different type of irregularity, your estimates will be wrong. Okay, so think of, for example, missing at random, missing at a block, different types of missingness. You need to train the neural network like that. So when we simulate data for the GNN, we simulate different types of of designs as well. Okay, we actually use a point process model for that, a cluster point process model, so that we simulate these sorts of patterns, which we are seeing, right? Anyway, so we do all of that, we train a neural network, and then we get estimates of the length scale, the variance, and the measurement error variance globally. And so these are the parameters, and also we can get credible intervals because we minimize the loss function. Okay, and all of this in just a couple of minutes. And you can apply this, of course, every day. All right, models of spatial extremes are not like Gaussian processes. They're much harder to fit. They have intractable likelihood functions, but from a simulation, from a training the neural network perspective, it's not hard because you can simulate quite easily from these models for spatial extremes, right? So I'm not going through what these models look like, but for the purpose of this talk, this particular model had 5 parameters. We did the same thing. In this case, we're looking at Saudi Arabia because some of my collaborators are from KAUST in Saudi Arabia. We're looking at PM 2.5. So again, it's really small boxes here where we could fit these spatial models of extremes in each of these grid cells. And then also do bootstraps. In total, we did 130 million fits, if you include the bootstrap samples as well. And all this was done in a few minutes as well, right? So, and even fitting one of these models using composite likelihood, you can't even do full likelihood, right? It takes a really long time. So this is a total game changer when it comes to models of spatial extremes. All right, let's look now at a POTS model and also at a case where, like I was talking before, we have missingness patterns which can vary. Now, the POTS model is a discrete spatial process model. It's 1 or a 0, okay? You may think of it as, I think it's called the Ising model in physics. And you've got one parameter which dictates how correlated the patches are. So if beta here is large, you get big patches of black and white. If beta is small, you get speckles, okay? And we want to estimate that beta parameter. The POTS model's got an intractable normalizing, the likelihood function has an intractable normalizing constant. So it's also a pretty difficult inferential problem. Right, but what I'm showing you here is that is a method which I'll call neural EM, which is robust to the missingness pattern, which is something that we want, because if you train a neural network on this sort of missingness, which is missingness at random, and then you give it instead this sort of missingness pattern, which is completely different, now it's a straight line, the blue was trained on this sort of data. We applied it to this. You can see now that it's got a lot of bias, right? So ideally, we want our estimators to be robust to missingness types. And there's an algorithm in statistics in the 1970s called the EM algorithm, the expectation maximization algorithm, which is provably, under certain conditions of the missingness cannot depend on the data, will converge to a maximum likelihood estimate. Okay, irrespective of your missingness type. Okay, so we developed what's called a neural EM algorithm. It's very simple. You've got your data with a gap in it. You conditionally simulate according to your model. Now, in our case, with a POTS model, it's a Markov random field. You can very easily conditionally simulate and fast. But if you don't know this, you could train a diffusion, like we talked about before. You generate lots of samples. These are independent and identically distributed. You do a map estimate, it's maximum a posteriori, and we approximate that with a neural Bayes estimator. And then you just keep on going round and round until you get convergence. And this is robust to the type of missingness that you have in your data. Okay? Now, side note, since these are IID, we used a deep sets architecture. I saw it listed in the previous talk, which is a way of dealing with exchangeable data in neural networks, because the output will be permutation invariant to its inputs, which is what you want when you've got an estimator of this type. All right. Okay, we applied it to ice cover in the Arctic. Okay, we've gone from the Antarctic to the Arctic now. Okay, so we just did this year by year, so we get estimates of this beta parameter as well as bootstrap confidence intervals. We can also then conditionally simulate, and you can see there's uncertainty there of whether there's ice or not in this boundary over here. And I mean, you probably don't need any of this to know that the ice cover in the Arctic is going down. pretty dramatically. In fact, the uncertainties are so small we can't even see them in this case. So you don't need neural SBI for this, okay? It was just more like a case study, but this is pretty alarming, what's happening in the Arctic. Okay. I'm not going to talk too much about this application. We've also applied it to estimating friction coefficients and bedrock under an ice sheet. So an ice sheet model is a pretty complicated set of partial differential equations. You can run them. If you change the bedrock profile and you change the friction coefficient under there, you're going to get different trajectories of your ice sheet. So black here is what it happened 20 years ago. Light gray is what's happening today. Okay, so it's retreating in this case. And now this is highly parameterized, this model. So I think we've got 250 parameters for the friction coefficient, 250 parameters for the bedrock. And again, we just trained a neural-based estimator to give us estimates from this model. Okay. In this case, simulation was a constraint. We didn't have, the simulation budget was a bit restricted because simulating these ice sheet models is really expensive. Right, so the final application before I conclude is related to a data simulation example. I heard there was a question before on whether we can apply this for data simulation. This is one way in which we can do it. There are many other ways. I'm going to keep it pretty simple by framing it in the terms of the integral difference equation that I shared before, but you could apply this to a really complicated atmospheric, like full PDE model if we wanted to, but we haven't gone down that route. So let's keep it simple. This is the integral difference equation. So yt plus 1 is a convolution of yt. Okay, we're going to add an error term later. And what we're going to say is that the kernel is spatio-temporally varying. So you've got diffusions, which are changing in space and time, and also advections, which are changing in space and time. All right. Right. So this model is very highly parameterized. If you throw it, sequential Monte Carlo at it or MCMC, it's just going to take a really long time. You will get there eventually, but it's going to take a really long time. So inference is really quite difficult. And this was considered a long-standing challenge in spatial-temporal statistics in how can we make inference on these parameters quite quickly. All right, so the idea is let's construct a neural estimator, which takes in now not only the present time point, but also the previous time point. And you need to do that. You can't estimate dynamics from a single snapshot. You need at least a few time points, right? So let's say we give it 3 time points in this case. So tau here is 3. And we train a neural network such that from these 3 snapshots, it gives us estimates of how the diffusion and the advection parameters are changing over space. Then we can use that to forecast what's going to happen at the next time point. Okay, and then you can actually just put this in here and you've got a generator of what's going to happen over time if you wanted to. All right. Right, so what is happening is our kernel, we've replaced theta, which are our unknown parameters, with their estimates. We call this plugin. In statistics, we use it a lot, okay, which it's a point estimate. But this point estimate, remember, an estimator is a function of something, right? And in this case, we're playing a bit of a game. It's not a function of the data, but it's a function of the process values. We've actually plugged in the process, not the data there. And I'll show you why later. Okay, so effectively what we've done is profiled out, again, another technical term, we've profiled out the parameters. What was a linear equation before can now be seen as a non-linear equation, but only as a function of the process. There's no more parameters that you need to estimate. Okay, so a linear parametric model, we've converted it into a non-linear, essentially non-parametric without parameters model. Okay, and then we're going to add this discrepancy term, and we're going to assume we know what the parameters there are. And we're going to discretize this integral exactly like we did before. And what we get is this very nice model, which again in statistics we call a vector autoregressive model of order tau. Because remember, we had 3 time points there. Okay, so the neural network is integrated in there. Okay, I'm not showing you, I'm just saying it's a nonlinear function. Nonlinear neural networks are nonlinear functions, right? And then there's this nice trick you can do is to convert a tau order model into a first order Markov model by expanding the state space. It's really not hard, but it's a big equation, so I'm not going to show it here. But essentially what you end up with is a first order nonlinear Markov model. Now we've also got data, and we're saying our data is somehow related to our y, and there's some noise there. And now what we've got is a state space equation. Now, state space model, there's lots of algorithms out there for making inference with state space models. Okay, all you need is a AR1 process, in this case a nonlinear AR1 process, and a data model. And we can use a Kalman filtering type techniques. And in fact, that is what we do. We have an ensemble of members. You propagate them through your nonlinear equation. So now each of those is going through a convolutional neural network, the same one. So you have 64 ensemble members, you pass them through, you get your propagation, and then you do what's called the Kalman filter update, which kind of compresses those depending on what data you have observed, and then you propagate to the next time step. Okay, so this is a data simulation. Okay, it's data simulation where we don't need to know the parameters because we've profiled them out using the neural network. Okay, right. So we're going to look at sea surface temperature again, but now take into account these dynamics. Okay. So for this example, what we did is North Atlantic. We divided it into 19 boxes and extracted lots of mini images. This is reanalysis data. We could use these data to train the neural network so that from the progression, it learns what the diffusion and advection parameters are. Okay, so we did all the training, and then we did an out-of-sample test. Okay, by looking at what happens in the following year. We used 64 ensemble members for the NKF, and this is the thing. Everything we're talking about today is just computational. We're not inventing new inference methods, or it's really just speeding things up. So probabilistic predictions and forecasts for these 3 months on 19 zones took only 10 minutes on that very simple GPU, which is, again, total game changer. Right? And moreover, if we look at the statistical efficiency of these forecasts in the 19 zones, this is the relative performance. So everything bigger than 1 means it's doing worse than the model I've just talked about. The green here is what we would have gotten in terms of root mean squared prediction error of the forecast and continuous rank probability score if we fitted with maximum likelihood and did our forecast. Okay, this took 2 days on an HPC with 5 nodes running continuously, right? But you can see the results are exactly the same. It just took 100 times more time to get to those results. The orange and the purple here are what you get with a descriptive approach, which is very easy to fit, very fast. But when you've got dynamics and you don't take those into account, you're going to get a worse fit, right? Okay. So now what we can do with Neural SBI is estimate, fit really complicated models and forecast with them, whereas before it was prohibitive. Right? Okay, so that concludes my thought. I just want to finish with a couple of thoughts. So is Neural SBI a golden ticket or a red herring? So the golden ticket arguments is that yes, it enables fast inference. In the case of point estimation, estimators are optimal in a base sense, and you can do uncertainty quantification. Okay. Why should we be careful? The first thing is the amortization gap. So when you train one of these neural networks, it's very hard to know whether, how accurate it actually is. In the case of point estimation, how far away am I from the true Bayes estimator? You sometimes need many simulations, and you've got unpredictable behavior if there is model misspecification. So as Kyle said, when you have model misspecification, things get really hard. And there's no quick fix to when you've got model specification. All right. So there's lots of other topics which Kai kind of talked about already, so I'm not going to mention them, talk about them too much. But if you are interested in learning more about neural methods for amortized inference, we've got a review paper out in the annual reviews, which kind of summarizes a lot of the techniques, not all, which are out there today. Okay, so that's it from me. Thank you.